Section 5, Parallel Processing. 5.1, Using concurrent.futures. We're going to look at when it's beneficial to split a program into multiple simultaneous processes. Then we're going to see how process pool executor and future objects allow us to farm out tasks to worker processes.
Some programs are what we call CPU bound, which means that the primary factor which determines how long the program takes to complete is how fast the computer can run through its instructions. Interestingly, most programs that we use on a daily basis are not CPU bound. However, for those that are, we can speed them up by breaking them into separate processes that run on separate CPUs or separate CPU cores. This has the net effect of increasing the number of program instructions executed per second, which means the CPU-bound programs run faster. In some programming languages, we can see that same benefit by running multiple threads for a single program. However, as I mentioned before, most programs are not CPU-bound, so the creators of Python have chosen to optimize Python's threading system for the common case, which has the side effect of making Python threads not very useful for improving the speed of CPU-bound programs. Besides, it's easier for the operating system to optimize the execution of multiple processes than multiple threads within a process, so even if threading were a viable option, multiple processes would be a better choice for a CPU-bound program. We've already seen one very low-level approach to launching a process and communicating with it, in our discussion of the subprocess module. However, for cases where the reason we want to do that is because we want our program to be broken up into a bunch of cooperative processes that work together, Python provides us with a couple of higher-level toolkits that make things easier. The more abstract of Python's parallel processing toolkits is called concurrent.futures. The concurrent.futures module is designed for programs that can be structured with one controlling process and several worker processes, where the controlling process hands out jobs to worker processes and then collects and collates the results. That's a fairly generic model, especially for CPU-bound programs. So concurrent futures is widely applicable as it is simple to use. And it is simple. The basic usage is just to import it, create a process pool executor object, and then call that object's map or submit methods to send work to the worker processes. When we're completely done with the process pool executor and we know we'll never need it again, we call its shutdown method or allow the with statement to do it for us. The process pool executor will take care of all the twitchy details of creating and communicating with worker processes. When we call the process pool executor's map or submit methods, we're asking it to call a function with the given parameters, but we want that function call to happen inside of a worker process, not inside the main controlling process. That has some implications that might not be obvious. First of all, it means that the function and its parameters need to be pickleable, which is another way of saying that Python needs to know how to turn them into a byte string that it can send to the worker process. For functions, that basically means any function is okay unless it was defined inside the body of another function. For parameters, it means that most objects will work, but generators and a few other kinds of special objects cannot be passed. It's important to be aware that both the function and the parameters passed to it can easily bring along information we didn't intend to send and when they get pickled for communication to the worker process. If any of the objects we send to the process pool executor references other objects, those objects get pickled up and sent too. It's entirely possible to end up sending most of the state of our program. That's particularly worth noting when the function we're asking to run is a method of an object. If the function is a method of an object, the whole object will get pickled and sent to the worker process, which means that the function call will be happening with a copy of the original object as its self parameter, not the original object itself. Second, the return value of the function is pickled and returned to the controlling process. All of the warnings about passing parameters to the called function apply to the return value too. So for example, the function can't return a generator object, and if the return value contains references to a bunch of objects, copies of them will end up being sent to the controlling process. Third and finally, the concurrent.futures code that's running in the worker process needs to be able to import the modules that our original code was loaded from. That means we may need to use the if name equals main trick to keep the worker processes from getting stuck running complete copies of our original program when all they wanted to do was import the module to find the function they were asked to run. We've already seen the map method of the process pool executor in our example, but let's look a little closer. The map method takes a function as its first parameter. We can also pass it one or more iterables, which will be used to figure out the parameters for each call to the function. So if we ask the pool to map the foo function to the lists 1, 2, 3, and 4, 5, 6, the result is that foo will be called with 1 and 4 as its parameters, called again with 2 and 5 as its parameters, and called a third time with 3 and 6 as its parameters. There's no guarantee about which order these three calls will happen in, though. After all, they're likely to each run in different processes, and the relationship between the process scheduling and wall clock time is partly dependent on unpredictable factors. The map method hides that fact by waiting for all the calls to finish and produce their results, and then returning an iterator that over those results in the proper order. Sometimes the map method is too simple. What if we want to handle the results as each worker process produces them instead of waiting for all the workers to get done? What if we decide not to run the function after all? What if we want to run different functions in worker processes at the same time? For that matter, what if we want to pass keyword arguments to the function? We can do all that and more using the submit method. Each call to submit translates to a single call to the function that we pass as its first parameter. The rest of the parameters and keyword arguments we pass to submit are passed into the function after being sent to a worker process. So, for each time we call submit, one worker process calls one function with one set of parameters. Submit does not wait for the worker process to finish running before returning. In fact, it doesn't even wait for the worker process to start running the function. And so submit does not return the result of the called function. Instead, it returns a future object. A future object is in some sense an IOU for the result of the function. If we have a future object, we can use it to check whether the worker process has finished running the function, to get the result returned by the function, or even to set up a callback that will be called when the function finally does finish running. We can even use the future object to remove the function call from the queue of jobs that should be shared out to the workers. The done and result methods of a future object are the ones that we'll use the most often. The done method returns true if the job is done and false if it's not. A job is done if it was cancelled, if it raised an exception, or if the job function has returned. The result method returns the return value of the job function if the job completed successfully. If the job function raised an exception instead, the worker process will catch the exception and hand it back to the controlling process as the result of the job. In that case, calling the result method will re-raise the exception so that it can be handled properly, as is foo error in the example on screen at the moment. If we call the result method before the job function is done, the result method will wait for the job to complete before it returns. That can be very useful, but sometimes we don't want to wait indefinitely. If the job isn't done quickly, we want to go on and do something else for a while. In that case, all we have to do is pass the number of seconds we're willing to wait to the timeout parameter of the result method. If the timeout expires without the result being produced, a timeout error will be raised. There are a pair of functions in the concurrentfutures module that let us wait on several features at once. They're called wait and asCompleted. The wait function waits until all the features are ready to deliver their results, or until the timeout expires. Then it returns a set of features that are done and a set of features that aren't. In contrast, the asCompleted function returns an iterator that produces features one by one as they become ready to produce their results. This is, in many cases, the easiest way to deal with multiple features simultaneously. In rare cases, the done and result methods of future and the wait and asCompleted functions of the concurrentfutures module aren't sufficient to let a program process features at the proper time. For those occasions, it's possible to have the feature call a function when the result becomes available. We can do that by passing the function into the feature's addDone callback method. The feature will remember that function, and when the job function is done, the callback function will be called with the future object as its only parameter. The code in the callback function can then call the future's result method to get the return value or exception that the job produced. Take note that the calling function will always be called in the controlling process, but it might not be called in the same thread as the main part of the program. When we use addDone callback, we need to be careful of thread synchronization issues, which is a big reason to prefer wait or asCompleted when possible. Future objects also have a cancel method, which tries to tell the system that we don't want the call to happen after all. This is not guaranteed to work, because if a worker process has already begun the job, the cancel method will not be effective. If the job connected to a future can't be cancelled, the cancel method returns false. If the cancellation succeeded, the cancel method returns true. The concurrentfutures module is perfectly suited to farming out computational tasks to multiple processes to take advantage of the CPU power of multi-core and multiprocessor computers. The map, submit, wait, and asCompleted functions are usually all you need for that kind of task.
When the main limitation on program speed is how quickly the CPU can run code, splitting that program into multiple processes can help it run faster, at least on multiprocessor systems. A process pool executor handles all the bookkeeping that's required to create and manage worker processes. When a task is given to a process pool executor to be shared out to a worker process, a future is returned. A future allows us to cancel the task, to check whether it has been completed, or to wait for it to finish and retrieve the result. If the program we need doesn't fit into the send out jobs and collect the results model, we're probably better off working at a somewhat lower level using the multiprocessing module, which is the topic of the next video.